Good afternoon, one and all. And now this is the third session of second day, and we have with us Professor Saikat Chakraborty, IIT Kanpur. So at the onset, I welcome Saikat sir, and I also thanks for accepting our invitation. Uh, Dr. Saikat Chakraborty completed a PhD in electrical engineering from Memorial University of Newfoundland, Canada in 2006. Before completing PhD, he worked in Asia Brown Boveri Limited India and Vawa Atomic Research Center India. After completing PhD, he worked as a special scientist at University of Cyprus, and first as a research associate and then as a lecturer in Queensland's University of Technology, Brisbane, Australia. Since 2009, he has been working in the Department of Electrical Engineering, Indian Institute of Technology, Kanpur, where he is currently a chair professor. His research interest includes power system state estimation, power system dynamics and stability, modeling of power system loads, smart grid and microgrid. Other than as a active and teacher and researcher, he is also very active in professional activity, and presently he is editor of IEEE Transactions on Power System, editor of IEEE Power Engineering Letters, associate editor of International Journal of Electrical Power and Energy System elsewhere, and associate editor of IET Generation, Transmission and Distribution. So this is the brief intro of Saikat sir. Now I request to Professor Saikat, please hold the fort and go ahead.
Thank you, Arvind, and very good afternoon to all of you.
Good afternoon.
All are doing fine?
Yeah.
Can you see my slide?
Yeah, sir, quite visible.
Yes, sir. Yes, sir.
Okay, so let me put it into presentation mode. Okay.
Yeah.
All right. See, this talk is about a smart city pilot project that we did in IIT Kanpur. Let me do one thing. Maybe I'll switch off the video. That way, probably the transmission will be good. Okay. All right. So this smart city pilot project was sponsored by the Ministry of Power, and the basic functionalities are complete now, and we are fine-tuning certain activities here. Okay. You see the map here. There are 14 locations here, and actually out of those only 12 reached execution stage, and these were the smart city pilot projects sanctioned by the Ministry of Power in 2014. And IIT Kanpur was the only academic institute. The rest of them were actually utilities, and the funding was like that. I mean, 50% came from the Ministry of Power and 50% had to be contributed by the executing agency. Okay, so it is equally funded by Ministry of Power and IIT Kanpur. And we looked into only the electrical aspect of smart city. Okay, so that's why I specifically mentioned here it's the electrical aspect we are talking about. Okay, because when you talk about smart city, many things may come into picture. You can talk about smart vehicles, smart roads, smart building, many things. But the funding was limited, and we only looked into the electrical aspect of smart city. Okay. By the way, you can interrupt me anytime if you wish. Okay, if you have any question. All right. So a little bit about this project objective and scope. The installation site is IIT Kanpur. The campus is around those of you. Dr. Arvind was here for a long time. and he knows that it's a 1,000-acre campus, approximately 4 kilometers square, and close to 10,000 people as of now live here. Of course, not now because of this corona situation, but the population is continuously growing. And the objective was to identify the challenges in setting up a smart city prototype, especially in the Indian context. Okay, why Indian context? Because there are certain technologies which are available in India or which can work only in the Indian environment. For example, if you straight away buy an inverter from maybe Europe or North America, uh, where the weather is much better, or pollution is much less, which that may not work in Indian environment. So those situations we have to keep in mind. And this pilot is working as a test bed for research and development activities, and it is a training platform also for utility engineers and academicians. We have an MOU with the Ministry of Power. We conduct training programs every 2 times every year. Okay. A little bit of project highlight. I think we had one more slide. Um, these are the basic functionalities here. Okay. If you look into the entire project, there are mainly 4 key components. One is the supervisory control and data acquisition system. We have 11 number of substations in our campus. We receive power at a 33 by 11 kV main substation, and there we have 3 transformers of 10 MVA each, and then that 11 kV underground cable is distributed throughout the campus, and then we have distribution transformers of 11 kV by 415 volt. Okay, and the entire distribution system is underground. Then we from the outside, outgoing of the 415 volt side, we can take the cables out, and we connect it to feeder pillars, and from there it is distributed to individual houses. So all these substations, we have installed a remote terminal unit. So the entire 11 kV network, including 33 kV and the 415 volt outgoing feeders at the 11 kV substations also, they're under SCADA now. We can monitor and control the entire distribution system. Next, we have advanced metering infrastructure. So some of the houses, I believe now we almost have 50 to 60 installations, including houses and major academic buildings, labs, etc. They have smart meters installed. And along with the smart meter, we also have the associated communication infrastructure and IT infrastructure. Okay. See, when we talk about the smart grid, it's basically the superposition of communication and IT infrastructure onto this electrical infrastructure, correct? So, and our AMI system is actually having capability to integrate up to 5,000 meters. So the plan is that in future, if we have sufficient funds, then we can replace all the meters in residences and buildings with all the conventional meters with smart meters. The third thing is a very unique that we did in this project. I don't think anyone else has done this in India, not at this scale at least. We went inside the houses and implemented a home automation system. Okay, why this is needed, we will come to that. It means we have some control over the appliances within the houses. Okay, we can control your refrigerator, your air conditioner, geyser, even fans, lights, etc. Okay, so that's the home automation system. And also we have chosen 20 houses part of this project, and we had installed a rooftop PV 5 kilowatt each PV system, okay, on top of those households. So 5 kilowatt peak solar PV was installed on top of those buildings, rooftop solar PV, and that is also integrated. And then all these 4 components, they are seamlessly integrated at a control center. We have a full-fledged smart city control center. And there we have a system integration platform which works on a enterprise service bus architecture. That's a modular architecture, independent of proprietary communication of the of different vendors. So we can just plug in your device in that architecture. Okay, so it's a system integration platform where all these 4 components are integrated. Why are we integrating? We will come to that shortly. Okay. And by the way, this integration was not an easy task. Okay, on paper it might look easy, but if you look carefully, all these 4 components, they're very different in nature. SCADA, data, property, refresh rate, etc., and very different from AMI data. That is different from home automation system, and also the data that we get from the PV inverters. Okay, so integration of all these 4 components is not easy. And then this platform is working as a demonstration, hands-on demonstration facility for utilities and industries, okay, and also for academic institutes. A little bit about the electrical system that we have. We already touched upon these. We have RTUs installed in all the substations. And AMI is actually not only 20 houses, as I mentioned, almost 50-60 installations. We have AMI now. And not only 7, all the student hostels are covered with smart meter now. So these are the basic functionalities we are working on in this smart city project. Smart home, advanced metering infrastructure. We have upgraded some of the substations. Okay, see, if you are retrofitting an old substation, what happens? Sometimes the devices may not be communicable. For example, you are trying to communicate with a circuit breaker, but it's a very old breaker. There is no option to communicate. So, if possible, we try to make those breakers communicable. When everything failed, we had to replace the breaker. So that retrofitting was done in the substations. Okay, we have a full-fledged smart city control center. If you happen to visit IIT Kanpur, you're very welcome to visit. You can have a look. Renewable integration is also a very significant part. Faculty members and researchers are working on converter technologies to integrate the solar power. Not only that, how to control that, right? Advanced IT infrastructure, why this is needed? See, the moment you have smart meter, SCADA, etc., at the end of the day, what is happening? You are dealing with a tremendous amount of data. Okay, so you have to have a IT infrastructure to manage that data, or store or manage that data. So you need to have an IT infrastructure. So in the control center, we have a server room. It's a separate room that we have, and we have the dedicated IT infrastructure to store and manage and visualize this data. And as I mentioned, it is on a modular architecture. Storage management. Some of the houses installations, they also have battery. So battery management system is also part of these project. This is the overall system architecture that we have. One thing, this is our SCADA, and let me put my specs. And these are the substations, RTUs, smart meter. In the control center, we are getting data from different domains. We are getting data from RTUs. We are getting data from smart meters as well as home automation systems, smart meter, RTU, home automation, even from the solar PV monitoring system. The inverters are communicable inverters. Okay, so we are getting data from all these 4 components in our control center. And if you have already noticed, throughout the system, we have to have a communication medium. Fortunately, in our campus, we have a very well-laid Ethernet network already in place. So we made full usage of that. Okay. But having said that, it's not that this kind of setup will work only when you have a Ethernet architecture. No, the directive from the ministry was that we do try different communication technologies. So we did that. We'll come to that. Usually, the communication medium that is available outside the campus in a city or even in remote villages, it's a GPRS communication. So that also we tried. Okay. The only reason why we went for this Ethernet was that already it is there in our campus. Okay, so that made our job easier. So these are the stairs and basic. We'll go to each of the domains one by one. These are the basic functionalities of SCADA. These are very standard functionalities. If you install a SCADA in your system, these are standard features utilities are having. Okay, communication with RTU, data processing, historical data storage, uh, control command transfer to RTUs, etc. Okay, and this graphical display is a very important part of it. Okay, we have a big monitor where single line diagram of the system, entire system is demonstrated. Okay? And also you can control, you can close or open your switch gear using the SCADA. Okay, so that's a very big advantage sitting from the compared to the conventional way the utilities are operating. See, the SCADA was not very common in distribution systems, but slowly things are changing, especially when we are having a lot of renewable energy sources. The utility or the distribution system operator wants to know what is going on with the renewable energy sources, and also consumers are participating in the operation of the system now through demand response programs. So distribution SCADA is becoming more and more important nowadays. In fact, many, a number of utilities in India, and they are having SCADA at their distribution level now. It's not only limited to transmission level anymore. Now, this is the SCADA architecture that we have in our campus. One thing I'd like to mention here, just because we are an academic institute, it does not mean that we could do things in an ad hoc manner. And that's usually what we do in our labs, okay? So we had to do everything as per industry standards because the very idea was that we are developing a prototype smart city, at least the electrical part of it. So we could not do any ad hoc thing here. Okay, whatever you do, that should be replicable outside our campus. So we had to go for standard protocols, equipment, etc. So what you see here is the SCADA architecture, very standard SCADA architecture that you find in a standard utility. Okay, this is the RTU, and our SCADA vendor was Synergy. I don't know if their name is written somewhere. Synergy. Okay, so this was our SCADA vendor. This is an Indian vendor and indigenously developed RTU, remote terminal unit. You see these blocks over here, they are multifunction meters or transducers. Okay, so these transducers, they measure voltage, current, power factor, etc., or sense the status of circuit breaker, whether it's on or off. And these status are sent to the RTU through Modbus. And from RTU, this data is transferred to SCADA LAN. Okay, here we are using it in optical fiber Ethernet infrastructure that we have in our campus, and we're using industry standard protocol IEC 104. Okay, and then all these measurements, by the way, they are GPS synchronized. This is again a very standard feature. Using network time protocol, this GPS clock synchronizes all the SCADA measurements at regular intervals. Okay, so from RTU we can pull the measurements every 2 to 3 seconds. Okay, so every 2 to 3 seconds we can get the data from RTU. Right, then it goes to the control center, and then it's up to you what you do with that data. All right, so remember this figure, 2 to 3 seconds. We get the data from RTU. We'll come to this. You can let me know if you have any question. This is a picture of the control room that we have. You can see the single line diagram of the system. This is our entire distribution system. These are some analytics that we developed. This one, as well as this one. Some weather forecasting model is integrated because we're also working on load forecasting. Okay, so if you have the historical data, you can make use of it in your load forecasting program development. Okay, so many things we are doing. We will come to those research topics shortly. So this is one single line diagram of the entire campus. So you see all the relevant information as demonstrated here. You can see the bus frequency, you can see the bus voltage, whether the breakers are on or off. These are breakers. Okay, the entire single line diagram is demonstrated here. All right. You can actually zoom into individual substations and you can see what is going on there. All right. You can do various kinds of analysis like trend analyses and so on. This is again some analytics, or I think it's a zoomed view of one of the substations, substation number 4. Okay. So then let's move on to our next subsystem, that is advanced metering infrastructure. So AMI includes not only the smart meters, also the associated communication infrastructure, as well as the IT infrastructure to store and manage the data. The smart meters are supposed to be Indian standard 16444 compliant. When we did those installations 2-3 years back, unfortunately none of the meters were certified because at that time the smart meters were coming into Indian market, and there were a long queue in the testing agencies. There were only 2 testing agencies. One was in IRDA and the other one is CPRI. There was a long queue, and at that point there was no certified meter. But having said that, these meters what we have, they do follow the compliance levels that are specified in this standard. Okay, and there are very standard features like net metering, tamper-proof, remote connect, disconnect. This is a very important feature of smart meters. Something interesting happened a couple of months back in one of the utilities in North India. We were part of the investigating team due to some faulty protocols or procedural problem in the AMI. What happened? One employee could disconnect a few lakhs of meters. So that was a big problem. Even at the political level it went, and investigation was going on. So what happened was that proper precaution was not taken. Who should be operating, or the standard operating procedure was not followed. Okay, so that was the problem. So one has to be very careful when using this remote disconnect and connect features. So one wrong command and lakhs of meters may be out of action immediately, and that might cause many problems. Tamper-proof is actually a interesting feature that we find in meters probably only in the South Asian countries. If you take a smart meter in North America or Europe, probably you don't get this feature. So anyway, so that's an interesting feature. A lot of research actually goes into this temper proofing thing. You do a research, come up with a new way of making it temper proof, and people can find another way of overcoming that. So that's a continuous struggle. So, and another key feature of the smart meter is that it has to have a connectivity. So this is there, and then you have to have a smart meter network. Okay, these are data concentrating unit. Typically, what happens? Several smart meters, they communicate to a data concentrating unit, and from the data concentrating unit, data is transferred to the control center. Okay, so that kind of is a very typical architecture. And then you have to have a metadata management system. This is very critical because, by the way, smart meters typically, if you are talking about utilities outside, usually get data every 15 minutes, let's say, from the smart meters. In our campus, since we have flexibility, we are getting data. We have set the resolution as every 5 minutes. We are getting data from the smart meter. So this data, if you recall, compared to SCADA data of 2 to 3 seconds, now it's 15 minutes or 5 minutes. Okay, it's much slower. Protocols are also different. Okay, usually the smart meters are DLMS protocol compliant. Then there has to be an integration of this meter data with the SCADA. So why we have to do this? See, this needed if you are trying to implement the demand response. What is the demand response? So demand response is something where the consumers take an active role in operation of the utility. Let's say there is a peak demand period. The utility is going through a peak demand period, maybe let's say summer time, and maybe 2 p.m. in the afternoon. It's a very hot afternoon, and a lot of people are using air conditioners, so demand is high. So that time, utility is borrowing a lot of power. Now, utility has to pay more, of course, to whoever is borrowing power from. As a consumer, if you consume more during that peak time, you actually have to pay more if you're under differential tariff scheme. But then what you can do, the utility during the peak demand period can send a signal to you. It can be done in an automated manner or on a voluntary basis. It can ask you or request you to switch off some of your loads during that peak demand period. So you might like to switch off your air conditioner maybe for 5 minutes. Doesn't cause a huge discomfort because in just a 5 minute the room is still cool and so on. Okay, so it's what is the benefit for you? You actually have to pay less. So that's the advantage. It's a win-win situation. The utility is a gainer, you're also a gainer. But one thing that you need to do here is, first of all, you need to know what is your consumption. So you need to communicate with your utility, needs to communicate to your smart meter. Not only the smart meter, it has to know what is going on inside your house. So home automation is needed, and also you or utility should be able to control the appliances. So therefore, home automation is needed. We'll talk about that shortly. And then we have to have an IT infrastructure to manage the data. All right. So then this is the overall structure of AMI implementation. We have smart meters, and the different types of communication technologies are actually listed here. Right. So see, we have a very typical or very special arrangement for placing the smart meters in the residences here. Usually, when the utilities install smart meters, usually they're kept outside the houses on the walls. But here, from the DCU to the smart meter, there are 2-3 walls in between. So there were signal quality problems in many places. We had to use repeaters. So those were very unique experiences that we had. So if you go to the next module, that is renewable integration, the houses, we had chosen 20 houses. In fact, 19 plus 1 is our control center. So 20 in total. Apart from that, also we have significant presence of solar PV in our campus. So we have, I think, around 2 megawatt of solar now in IIT Kanpur campus. Our peak load is 10.5 megawatt. But within this particular project, we implemented 100 kilowatt of solar. And the inverter that you see here is, we call it grid tie inverter. Grid tie in the sense, if the grid is gone, the inverter stops working. Okay, so that's the most common type of inverter that is available in the market. Usually the solar power plants also that you see, if the grid is off, plant is off. That's, unfortunately, that is the reality in your houses also. If you have rooftop PV, almost invariably, if the grid is not there, then solar PV stops working. The problem is that if the grid is not there, it doesn't get a reference. Okay, so somebody has to generate that reference. So if you have a battery, then you can make the solar PV work even if the grid is not there. So that we call, that kind of inverter we call hybrid inverter. And we also have these hybrid inverter in 4 of the houses. Okay, this is one such example house, not my house, it's not so well kept. So we have 5 kilowatt peak each solar PV on top of these houses. 4 houses are having hybrid inverter. So these inverters, these setups, in fact, my house is one of these houses. My house has become a lab now. These inverters, they can work off grid, in the sense they're connected to battery, they're connected to grid, as well as to solar PV. Now, one big advantage is that the battery injection through the inverter can be controlled. So thereby the house can participate in the demand response program. Okay, so inverter injections are controllable. So these battery connected solar PV systems, they can fit to grid as and when it is required. All right. Otherwise, also when the grid is there, the system works like this. It serves the load within the houses. If there is anything extra, that is pumped to the grid. So that's how it works. And these installation that needs to be cleaned every let's say 2 weeks, because we have a very high level of pollution here. Dust particles, bar droppings, and they accumulate on those panels. Okay, so they need to be cleaned. And by the way, this is a very significant thing. We have observed that if it is a lot of dust, if it accumulates on the panel, the efficiency goes down drastically, almost goes to half. So it needs to be, cleaning is a very important thing. If you have a solar panel on your rooftop, please make sure you are cleaning that. Okay. And the tilt that you see over here, tilt is approximately equal to your latitude. Okay. Something to do with the geometry or the axis of rotation of Earth, correct? Okay. So then we have come to the next module that we have is smart houses. So within the houses, we have a central controller. It's actually a tab. And in that tab, we have a number of applications loaded. So through those applications, we can actually control the loads within the houses. Okay. And thereby the houses can participate in the demand response program. So what we had to go through that, how do we do that? We'll come to that. Before that, these four things were actually integrated into an system integration platform. So all these four components are integrated here. We have data from all components. Then you take whatever control actions you would like to take. Okay. Now, there were certain challenges within the houses when we went to install those home automation devices. We figured that the existing distribution box would not work. So we had to replace the distribution boxes. Okay. Segregated the essential and non-essential loads. Okay. So the figure that you see here is the customized distribution box for individual houses, and the scheme that you see is our solar PV integration scheme. Okay, both for hybrid inverter and grid tie inverters. Okay, so here in the distribution box you will see two rails. This is number one, number two. So these two rails are buses. One is for, this is for the top one is for non-essential loads, the bottom one is for essential loads. Okay, what we understand by essential and non-essential. See, by essential, we are classifying the loads, for example, lights and fans. Why do we call them essential? Suppose you are working in a room and suddenly somebody switches off your lights and fans. It causes huge amount of irritation and discomfort, isn't it? So we don't play with that. So that is essential load. Of course, we can play with that if you want, but usually we do not take that into account when we are implementing demand response. The second type of load, usually these are high power loads. High power means you are plugging into those 15 ampere plugs, and the essentials are usually 5 ampere devices. Okay, so these devices, for example, heavy washing machine, refrigerator, large refrigerator, geysers, air conditioners, correct? So these things we are taking as control level loads. So in the utilities or at the main substation, if we are going through a peak demand period, we can control these devices through these Wi-Fi control level switches, which are placed in this distribution box, and also adjacent to the appliances. Okay, wherever the switches for the appliances are there. So we have a small wireless module connected to each switchboard within the house, and from those switchboard we can actually control the appliances. So that's how we are able to implement demand response, right? Having said this is the segment where we encountered most of the challenges. The technology is not yet mature, not at least in India, or it was not mature at least at that point of time. See what happens on paper. People will say that we can always, and the vendors will say we can provide you the solutions. But when it comes to reality, when we implement or install that, then only you will see the problems. Okay, for example, the wireless switches, we had a very strange problem. The polarities were getting reversed. So then we figured out it was actually connected to a fan, ceiling fan. So the moment you switch on a fan, there's a back EMF that was switching off the switch, that transient. So we had to take care of that. So those are challenges that you have to go through when you are implementing these new technologies. Even if you are making a switch, it takes a long time to make it robust and reliable. These are learnings from these executions. So this is our overall system integration scheme that we have. All four components are integrated. These are some dashboards, software dashboards. I think these are developed by researchers in our lab. It shows you cumulative or per day consumption, power factor, how much you are getting from the solar. Those analytics are there. Now, basically, we are a research organization, so the biggest advantage we are having after installing this, implementing this project is that the students now can test and validate their algorithms in the field. Okay, so they can implement their algorithms in the control center and validate. Okay, so that's a very big advantage that you are having now. So people are working on remote monitoring and control applications for smart homes. Distribution state estimation is another area we are heavily investing. We are developing algorithms to, for example, we can estimate the distribution line parameter, cable parameter, for example, using SCADA measurements. Okay, so, and in fact, we are also doing some work with CESC Kolkata to identify line parameters for one of their transmission lines. And the algorithms were actually developed here in IIT Kanpur test bed. Okay. The problem here is that you have a very limited number of measurements, SCADA measurements, if you are using. But the challenge in distribution system set estimation are manifold. Why? Because usually you have to consider three phases. In transmission, usually it is balanced, so you consider single phase estimation. But in distribution, it can be heavily unbalanced. So then you have to consider three phases at the same time. So it's a three-phase estimation problem. So some specialized techniques need to be there to estimate the states or parameters, line parameters. Load forecasting is one area we are using. We are working on because we have a significant amount of historical data that comes from meters. Okay, meters and SCADA RTUs. We are working on distribution reconfiguration. Means you can actually, we have breakers which acts like a RMU in certain places. We can basically, they are load break switches. So we can choose an alternate path for your distribution system to supply the consumers. So a choice of path actually can have many motivations. For example, you can try to reduce your losses. You can try to reduce voltage deviation, etc. Okay. And you can run the algorithms in your SCADA in your control center, and then you can send the commands to open or close the breakers. So that's visible now. Fault detection, isolation, restoration, it has become much easier with the implementation of the monitoring mechanism. Otherwise, somebody had to move around, in a system with those fault locators, handheld devices. That is no longer needed. Of course, you have to design your algorithms for that. That's something we are working on. Intelligent billing system, few students are working. Demand response management, this is one key area, and this is exactly where this home automation comes into picture. Home automation. So we are able to control the appliances and demonstrate demand response methodologies. And also, faculty members in power electronics, they're working on efficient design of the sort of PV converters for off-grid and on-grid operations. So these are some of the activities that are ongoing based on the platform that we have. Okay. So dashboards that we have, some are cumulative data, some are instantaneous data that you see. Many kinds of analytics are possible. I think these are homegrown. That is, in our labs, they created these things. And some analytics are also provided by the vendors. Now, one important thing here, even at the engineering stage, we had to make sure that whatever standard installations or software that we get from the vendors, for example, SCADA software, AMI software, we should be able to implement or integrate our programs or our algorithms into that. Okay, so that was ensured in the tendering stage itself. So if you are planning to have this kind of setup, make sure you are able to play with it. Important. Otherwise, what will happen, you will not be able to implement your algorithms. So that's ensured. These are some more consumer dashboards. I think this data of one particular house. And using Google Map, our researchers or students, they develop some application. This is not exactly GIS, but you can have a feeling of where exactly things are there. Okay. If you zoom it, I think my house is somewhere here. Okay. And this is the, okay, let's see. Okay, the control center is over here. Okay. And my house would be somewhere over here, and these are other installations where the solar PV are there. And they have also a legend. These are substation locations, 11 kV substations. You can see the locations of 11 kV substations. And this is our main substation. Okay. And then underground 11 kV cables, they run throughout the campus. Okay. This is one app for home automation solution. You can actually drag these things to reduce or increase the brightness of light, etc. You can also use voice interactive devices like Alexa and so, and you can integrate that with the home automation system and so on. Okay. So that's all. If you have any question, please let me know. Anyone has any question?
Please ask if you have any query. Participant. Anyone?
So I hope I did not make everyone to go to sleep.
Avinash, please ask.
या सर अभी क्या हमारे सिस्टम में ऐसा इन्वर्टर अवेलेबल है जो ग्रिड ऑफ होने के बावजूद हमारा वो होम अप्लायंसेस को पावर प्रोवाइड कर पाता हो?
हाँ, अभी मार्केट में आ गया है, but it's not very common, but there are some vendors which can give you these inverters now. Okay, but it's not very common. It's somewhat difficult to get these inverters still now. So we had to go to the vendor's place and had to do a lot of customization. Okay.
Okay. And sir, अब ये प्रॉब्लम जब मैं 2012 में नाइस में था, मैं नेशनल इंस्टीट्यूट ऑफ सोलर एनर्जी में, that time I was seeing every inverter having a problem that when you are using the inverter and solar inverter and grid integrated system, then you are solar power system. The inverters are limiting the solar power for about 10 ampere or 5 ampere, maximum 5 ampere, and the remaining are taking from the grid. So that type of solution, that type of problem has been solved till now or not, I don't know. That's
See,
why
these inverter usually they operate under MPPT mode.
Is maximum power which are having generated by the solar module at MPPT, whatever these modules are working and MPPT, whatever they are at MPPT, these inverters are not collecting all that generation also. not connecting that.
Time probably that problem was, but this problem is now solved. I think inverters, grid tie inverters, at least they are fairly available in the market. Even I mean, I have seen in my house it goes up to 4.5 kilowatt from a 5
They are
kilowatt.
using maximum power.
Power. Yeah, from a 5 kilowatt setting, you can get up to, let's say, 4.5, something like that.
Okay.
So it is possible. But the only thing is that you have to keep cleaning the panels at regular intervals.
Yeah, solar model dusting problem is very much that time also, and till
Yeah,
now they are working on that also.
correct. So its technology is still evolving.
Thank you, sir.
Mhm.
Anyone else?
Any other question? So this is an online workshop or there are physically present participants?
All are online, sir.
Online, I see. Okay.
Even there is no student in the campus, sir, right now.
Okay. So how is everything? I mean, your online classes are going on.
Yeah, online class.
Okay. Okay, any other question? You can email me. I can give you a handout based on the slides. If there is an interest, you can distribute.
Yeah, sure.
No, I'll do that. And if there is any question, you can always email me.
Yeah. Sure, sir.
चलो ठीक है फिर और कोई क्वेश्चन है?
नहीं सर, थैंक यू.
अभी तो नहीं आया. So, sir, is this the last slide, sir?
Yeah.
Okay. So, thank you very much, sir, for enlighten us regarding the very latest topic related to that smart city project.
Yeah, thank you. And all of you, if you happen to visit Kanpur, please visit our campus and see what we are doing.
Yeah, sure. So, I hope, sir, you will accept our invitation and enlighten us regarding the latest technology.
Sure. I would like to go there physically once this.
Yes, definitely.
Session is
We are
over.
very much interested, sir, to call you here, sir. And definitely, I think in 2021, there may be favorable conditions. We will
Yeah,
encourage.
hopefully. Let's see.
Okay, thank you very much.
Okay, thank you, everybody.
Thank you, sir.
Okay, thanks.